Okay, welcome. So this will be kind of fun. We're finally getting to Chapter 3, which is our first foray into less, generic science and math topics, and more specifically chemistry topics. So now I get to talk about the atom. Pictured here is the atom, the superhero. My idea of some sort of nerd pun. And so I guess we'll go ahead. So I'm going to talk about what makes up the parts of an atom. So here we go. So yes, I have comic book joke and then a riff on a Jewel album in successive slides. So there we go. So we talked at the very beginning about what chemistry is all about. And we said that chemistry is all about matter, right? So we need to talk about what matter is made up of. This has been debated since a long time ago, since 6th century BC. And the idea of atoms is usually attributed to a Greek philosopher named Democritus. Democritus thought, it was really part of a debate. The debate was basically this. If I take a piece of matter, anything, a piece of wood, whatever, and I chop it up, I chop it in half, now I have two pieces of wood. I take one of those halves and I chop it in half, and I chop that half in half and half in half, and keep going. Will I reach a point where can I chop forever? Or will I hit a point where I have the last building block, the last thing that can be considered stuff? Is there a fundamental piece of stuff that I can't break? So he argued that matter was discontinuous, that yes, you would hit an indivisible bit of matter, a bit of stuff that can't break, and you can't, chop it up. Now, I gotta admit, he had no evidence. He just picked that side. So he gets his name in all the history books and all the science books for coming up with the idea of atoms, because he thought of them apropos of nothing, but he had no evidence. He had no reason to believe. The guy on the other side, I have heard his name is Zeno, I barely know who he is. He had just as good a claim to say that, no, you could keep cutting forever, because neither of them did any, actual experimentation, so no one knows. So they were just guessing. I don't like to give Democritus too much credit for guessing. But he did pick a name. So he got a name, he got to name them, and so he called them atoma, which means uncuttable. The Greek prefix a is not or without, so uncuttable. And toma is to cut, so not to cut or not able to be cut. So modern theory does support the existence of atoms. There is now, since about in the 17th century, we started getting, in late 1700s, we started getting evidence of atoms. So it was finally put together in the 1800s by a guy named John Dalton, an English school teacher, came up with the theory that suggests that atoms exist. So an atom is the smallest piece of matter capable of sustained independent existence. They're the building blocks. Each element is made up of atoms. And so now in this chapter, we're going to talk about, and here's a nice picture of some atoms, we're going to talk about what these atoms are, what they're made of, what they do. And that's really going to be a lot of the core for where we build up from here. So I do get a chance to say Democritus is wrong, because he gave it the name atoma based on the idea that you can't break it apart any. This is not really true. And to give credit where credit is due, John Dalton, the original, the person who originally put together atomic theory, he didn't know either. It wasn't until later days that we knew that that atoms were made of the smaller bits, and you could actually break them apart. So there are some subatomic particles. So sub means below. So particles that are smaller than the atoms. Now, why we still consider atoms to be unbreakable, the smallest pieces of matter, because these subatomic particles don't exist by themselves for very long. They can't just hang around. So it's the building blocks for an atom. So in the same way that a rabbit, we can still consider them indivisible. In the same way that a rabbit has ears and eyes, they don't exist independent of the rabbit. So it has parts, the atom has parts, but they don't just float around independently any more than rabbits' ears come bouncing through the fields. So, my brain goes in very weird places sometimes. So there are 3 subatomic particles, and here's a big chart showing them all. And so here are the names, the symbol, charge, mass, and where they are. So the name of them, we have electrons, protons, and neutrons. Electrons, we give them the symbol E with a negative. So in all these cases, we usually give it a symbol starting with the first letter and then the charge. So the charge on an electron is -1. Now, I should say this. This is on a relative scale. So there's actually a unit of charge called the coulomb, and an electron is actually some tiny fraction of a coulomb. But it's easier just to count up charges in terms of electrons. Protons, P positive, have a positive charge, and the magnitude of that charge is exactly equal to that of an electron. Neutrons have no charge, hence the name. So electrons negatively charged, protons positively charged, neutrons neutral. But look at the mass. Take a look. Which of these? So 2 of them are the same. Protons and neutrons are about the same mass. Now take a moment. Look. Are electrons smaller or larger, or less massive or more massive? They're substantially less massive, about 1,000 times less. -28 is much smaller than -24. In any case, these are all really small. Location, electron cloud, nucleus. So the electrons, both the proton and the neutrons, so protons positively charged, neutrons neutral, hang out in something called the nucleus. And I'll show a little diagram of this in a moment. Electrons are negatively charged, and they hang around the outside of the atom in the electron cloud. So the nucleus is positively charged. Now, there are things in there that are neutral, but overall it's positively charged. So, let's take a look. So, particles not randomly arranged, I mentioned this already. Protons, neutrons are in the nucleus. Electrons are outside the nucleus. So the nucleus is a very small, very dense, positively charged center of the atom. So electron cloud is floating around outside. So I know I've been just kind of reading the notes from at this point. I'm going to actually do some drawing now. Well, I'm on a different podium than I usually am, so I can't figure out how to make these any bigger, so I'm just going to have to scribble a lot. So imagine this is the nucleus. Nucleus is this dense center. And the electrons are out here. Here's the electron cloud hanging out. And so the electrons are out here kind of in this electron cloud. And we'll talk at the end of this chapter. By the end of this chapter, we'll talk about what the electrons are doing. The nucleus doesn't really have this thing on here. It's generally spherical, more or less. Now, you've probably seen this. In fact, honestly, more likely what you've probably seen is this picture of the atom. You've probably seen this. You know, you see the nucleus, and you see this. I'm not very good at drawing it, but right, with the electrons hanging out here and here and here, etc. Can't get them all there. Anyway, so hanging out there. So that's not quite accurate, but I'll leave that for now. All of these pictures basically encompass the same idea. That at the center of the atom, there is this dense, positive nucleus where the protons and neutrons live, and then on the outside are the electrons all whizzing around super fast. So, one thing I want to really press on you is the difference of scale. And this is, you're probably not going to believe me when I say this. But if you could imagine that we took an iron atom and expanded it to the size of a football field. And here's where I can actually make this bigger. If you expand it to the size of a football field, so the whole thing, the electron cloud is now the size of a football field. So it's, 100 yards diameter. The nucleus would be a 4 millimeter little pea on the 50-yard line. So that you might be able to believe. So we're talking about a scale like, here's my electron cloud. It goes off the screen, and then there's my nucleus in the middle. And that's probably too big, actually. It's this little, football field size atom, 4 millimeter pea on the 50-yard line. Now here's the thing you're probably not going to believe me about. That pea, that little 4 millimeter sphere, would weigh 6 million tons. Now you might say, that's impossible, Steve. Nothing is that dense. Well, of course nothing is that dense, because the atoms that we experience in the world are both the nucleus and the electron cloud, right? So when I take a single atom and expand it that big, the real-world mass equivalent would be a sphere of iron that size. And maybe you can imagine a 100-yard diameter sphere of iron ranging 100 yards into the sky and 100 yards into the ground probably would be 6 million tons, right? That's a whole lot of solid iron. It's just that what I'm trying to point out is that most of the mass of matter is confined in this tiny minority of the space. If I took a desk, this desk is sitting in front of me that you can't see, and I compressed it down and just pulled out the nuclear material, now this desk in the classroom is really, really big, and I actually can't lift it. It's probably 300 or 400 pounds. But that, you wouldn't even be able to see all the nuclei combined together. It would still be 300 or 400 pounds, because almost all of the mass of an atom is in the nucleus. So this is all of the mass, or rather 99.9% of the mass is in the nucleus. The other 0.01% is hanging out here. And most of the space of the atom is from the electron. So most of the mass is confined in like 0.01% of the space. So it's kind of inverted that way. And we're just not used to thinking about it. In fact, there's a literary reference to this. I don't know how many of you have read the children's book Wrinkle in Time. At the end, Charles, the main character's brother, who I forgot the main character's name, Charles holds his hand up to a door and the door just vanishes. And what he describes as doing is he's compressing it all down to just the nuclear material. And he goes in at length about this exact phenomenon. So, the main point of all this rambling is to tell you that the nucleus is extremely dense. It's where most of the mass is. And the electron cloud is where all the electrons are, all the negatively charged electrons are hanging out, and they're responsible for most of the space. So in that same analogy where an iron atom has been expanded to be the size of a football field, what you would really have out there, you'd have this 4mm P on the 50-yard line, and then you'd have 26 electrons that are the size of mosquitoes but still weigh like 150 tons together. And they'd be whizzing around the outside so much, so fast, these 26 things whizzing around the football field so fast that they would seem like a solid wall. Very, very weird stuff, I know. So it's really kind of weird to think that an atom is mostly empty space. So why does an atom feel solid? Why does matter feel solid to us? So it really has to do with the nature of charge. So let me explain about charge real quick before I go into anything else. So there's two types of charge, positive and negative, which is sort of covered by mentioning that protons are positively charged and electrons are negatively charged. But that's really important to know. Opposite charges attract. Now, you may think, oh, this is a lot like magnets. And in fact, electrical charge and magnetic attraction are kind of one and the same. They're sort of two sides of the same coin. Positive and negative charges attract. Like charges repel. Positive, positive, negative, negative repel. So if you think about it, the reason things feel solid is that like say I'm walking on the ground, right? In my shoe, I have atoms on the bottom of my shoe. And the outside of these atoms have electron clouds as well. And so they're all negatively charged on the outside of the atom. Well, so does the ground. The ground also has negatively charged electrons. And so it's the electron clouds of my shoe and the electron clouds of the ground are repelling each other. And therefore, they can't occupy the same space. Right? So they can't move into one another. Gravity is the weakest force in the universe. Of the four fundamental forces, it's the weakest. Electromagnetism is much more strong. If you don't believe me, think about what happens when you drop something off of a building, right? It hits the ground, and it's only not going into the ground because of negative repulsion of the electrons. So gravity can't hold a candle to that. So The reason something hits the reason things feel solid is because of electromagnetic repulsion. One thing I want to say also is that charges cancel each other out. So now this is sort of in the case of if two charges, positive and negative, are closer to each other than an observer is from them. I'm going to draw a big creepy eye with eyelashes. This observer is farther away than that distance. They appear to add up. And that's because electrical charge exudes sort of a field, and the fields are overlapping mostly. So a positive and negative to an observer who's farther away than the distance of the positive and negative are from each other, it's going to look like positive 1 minus 1, which is 0. It's going to look neutral. If I had two positives and a negative, then it's going to look like plus 1. So this is why atoms end up looking neutral. Because if you have an equal number of protons and electrons, then the atom is going to seem neutral, right? Because the charges will cancel out exactly. But if you have an imbalance of protons and electrons, which we'll talk about a little bit later, they can seem like they're charged. So they cancel each other out. Okay. Atom is mostly empty space. Oh, I said all this already. I did that. Okay. Well, I think the last thing I have to say is just this thing about charge. So a whole atom is neutral. Sometimes we'll have charged atoms, but I'm going to get to that later. For now, let's think about atoms as being neutral. There's no net charge. And as I said already, in order for this to be true, positive has to equal negative, which means you have to have an equal number of protons and electrons. So if you have an atom with 6 protons that is neutral, then you must have 6 electrons, by definition, in order for it to be neutral. However, it still is important to know that the entirety of the positive charge is still in the nucleus and the entirety of the negative charge is still out in the electron cloud. So that's it. That's all I have to say about the structure for now. So there you go.